Go ahead, Mustafa.
Yeah,
There you go.
thank you so much, Hans, for the introduction. Hello, guys. I'm so happy that I will present you a hands-on session on mass transfer. As Hans said, let me share my screen. I hope you can see it, yeah?
Yes, I can see it clearly.
Okay, okay. So I stop my video and then solely on the slides. So the topic of the session will be some details of mass transport, things that you saw in the main course in the slides of Hans, and then a couple of other topics on computer methods and its application for relevant topics. So what we will discuss is indeed, first we will have a look at the transport equation in its general form, what it is intended to do, and this sort of stuff. And then what makes it a diffusion, a convection, or reaction equation, and maybe a combination of these things together. And then we will go for solving some of the problems that you saw in the slides in details manually. So as a reference for you to see how they can be solved symbolically, or let's say analytically here. After that, I will introduce you some of the techniques that you can employ for having to take advantage of computers in this regard. I will introduce you Python and Jupyter if you're not familiar with that. And then I will solve the problems that you saw that I've solved manually using these tools symbolically. And then we will go on with more difficult problems, for example, for non-steady state problems or transient problems. And I will demonstrate you the techniques of numerical computing as an extra, which is not indeed part of the course, but yeah, it might be interesting for you to see how things go on in real world problems. So I start with transport equation. The transport equation indeed describes how a scalar quantity is transported in space and time, let's say, its evolution. We can say in space and time, but the transportation is more in space. So it diffuses, it reacts, and it's advected, let's say. This equation is commonly used in transport phenomena studies. You know transport phenomena. You may have already passed a course in transport phenomena in biomedical engineering or in any other field of relevant fields in science or engineering. You know, heat transfer, mass transfer, momentum transfer, which is indeed related to fluid flow and this kind of stuff. And the transport equation is indeed the core, the heart of these topics. From a mathematical perspective, the transport equation is nothing but a differential equation. You know what a differential equation is. We can say more precisely a partial differential equation, which means that you have also partial derivatives in the equation to describe the conservation laws, how mass is conserved, how heat is conserved, this kind of stuff. Yeah, more technically speaking, the transport equation is called reaction diffusion advection equation. You have seen this in the slides, that how it looks like, but I have it here again. So if we have a function, a variable of interest, let's say here it is c, that is a function of space, coordinates x, y, z, and time. So in one-dimensional cases, it will be only function of x and t. In 2 dimensions, it will be x, y, and t. And in 3 dimensions, it will be something like this. But this can be, for example, a wide variety of different things, quantities, let's say, for example, it can be concentration and mass transfer in chemical engineering, or here in tissue engineering, or another example, famous example, can be temperature in heat transfer. So the equation consists of multiple terms. The first term shows how the equation, how this quantity of interest, this variable of interest, for example, concentration or temperature, evolves in time. So the partial derivative of that regarding time equals to how this variable, how this quantity diffuses. So we have diffusion term, how it is advected, and we have here the velocity. You can see that it is indeed related to advection, and then how it reacts with the world. So the reaction term has lots of different shapes, but for example, one common way of saying that, which is a bit different from the slides. In the slides, you had seen another form of that, Michael Minton form of that, but here it's a simpler way that, okay, if you have, for example, this reaction that is happening, that is occurring with the reaction rate K, you can say that the rate of change of concentration of C component regarding time can be written as this. So this is indeed how the reaction term looks like, but it can be also in other shapes and formats. You will see more examples in the slides, in the upcoming slides, let's say. As a short introduction to this equation, there is one video that I have prepared. You can access it on YouTube. So I will show you that. It's, I think, less than 3 minutes. Let me start it. So you can see the video. Let me see if I have it here. The video describes the way that this, how these mathematical symbols indeed are corresponding for various terms, for various phenomena in this equation. So this is indeed the video. In the video, you can watch it later, but in this video, I will show you that this equation is indeed written in this way, as you saw in the slides. And then U is a variable of space and time. But in this equation, we have a set of different mathematical identities. So we have gradients here. As you can see, so the gradient of a scalar function is indeed a vector of its partial derivatives. So in one-dimensional case, you can easily omit these terms, and you have only partial derivative to x. And then we have also the divergence of this of a scalar variable, for example, here or here. You can see that it performs on vectors, and then you have a scalar out of it. A combination of these two together will be the Laplacian, which is indeed the divergence of a gradient, and this is indeed the second derivative. So now you can see the similarity with what you have seen in the slides with these things. So for a simple diffusion equation, you have seen this format that the concentration changes regarding second derivative, regarding the x or y, and then for the convection, you have seen these type. And then I have prepared some, the terms as I showed you in the slide. So this is for the temporal evolution, how it evolves over time. This is for diffusion, convection, and then for the reaction. So, which can be also the source, how it is consumed or how it is generated. So a couple of examples on that. We have heat transfer in solids, the famous equation for heat transfer in solids, and the mass transport in corrosion process, which is indeed related to my PhD work. In this case, magnesium corrosion, and Navier-Stokes for fluid flow. And as you can see, the same pattern is here. You can see that the reaction diffusion advection equation can have different forms, really different terms appear, but they have all the same pattern. So the evolution over time, the temporal evolution, the diffusion term, as you can see, which is indeed related to the divergence of a gradient or the second partial derivative, and then the reaction term. And as you can see, for example, in a heat transfer equation, it's related to the source, how heat is generated. But for the mass transfer, for the corrosion case, you can see that it is very similar to the form that I showed you. And then the advection term, which is here only in the Navier-Stokes equation, it can be also very similar to that. can appear in other equations. But the thing is, this is just you know, as a minor note, that what is really nice in the Navier-Stokes equation is the U is indeed advected by itself. That's how how momentum is indeed transported. So make sure to check this out later, so you can have because it has also narration, so it is self-descriptive. Let's go on with these slides. So the convection effect. What is the convection effect here? Because it's a bit, you know, it might be better to have a visual description of that. So here you see two different two conditions. The initial conditions are the same. So I have one, let's say one sphere or a circle in 2D here that it indeed produces it produces ions, let's say, and it releases ions. And then I have one diffusion equation here, and then diffusion advection here. And I have V, an external velocity field, which is indeed from left to right. And then we want to see how it looks like if we solve these two equations. I will show you how these equations can be solved later on. But at this moment, I want to just show you how the advection affects the behavior of the system. So you see in a diffusion, it spreads in space. But for a diffusion advection, it moves, you know, the external field moves, transports the released ions, the released chemical components to the right. So this is indeed the effect of advection. But in addition to that, we have also, you know, for various speeds, it has different effects. So here I have, again, simulations. I increase the speed. Here, it's better to say velocity, the velocity of the external field. And I want to see, in this case, how released ions, released chemical components, or temperature, or whatever else is indeed transported. So let's have a look at it. You see that when you have a very slow velocity, it is you know, less chaotic. It is just transported to the right. But when we increase the velocity, it goes for a sort of turbulence or a bit of chaos, and there is also a new form of patterns that is formed. So this is indeed the effect of convection to this equation, to this transport equation. So this is indeed important, but yeah, that's the thing. So I think that's enough as an introduction to this equation. Let's go to see how we can solve the problems. This is something that you will face in the final exam. One example, indeed, maybe exercise, question to be solved by you. I will show you how to solve these things. Make sure to have more exercises on these so you get well prepared for the exam. So how we solve problems for simple equations manually, analytically. So the thing is, the first step is integrating the conservative form of equations to get rid of the derivative terms. Then we apply the boundary conditions. This is the most important step, that you should know how to apply it correctly, how to identify different boundary conditions. This will be indeed the main point of the question you will face in the exam. To obtain the integration coefficients, because you know from the calculus course you have passed that when you integrate it, when you have an integration of an equation, you will have integration coefficients. And in this case, you should apply boundary conditions. And in case of transient non-steady state problems, you need to apply initial conditions to get those integration coefficients. And then problem is solved, and you can go on and calculate the quantities of desired, and maybe you have asked for, like the maximum diffusion depth that you will see in these examples that I will provided you with. So for this case, for this presentation, I will have some steady state examples that you saw in the slides. So make sure to solve all the examples that you saw in the slides in the main course. and solve them analytically to be sure that you know how the final solution is indeed derived. As the first example, I will go to the case 3 in the Hans slides, which is indeed one-dimensional diffusion in a cellular construct. So the thing is, we start with this equation. In the beginning, but then we want to see how we can get this form, which is indeed the solution to this regarding the boundary conditions that we have here, and then we want to have the maximum diffusion depth that in this case the oxygen can go. So the problem to solve is indeed the following equation, which, as you have seen in the slides, as you already know, it correlates the consumption of oxygen and also the density of the cells and the diffusion of that to the evolution in time. So we have one-dimensional case, so make sure to understand the boundary conditions correctly here, that what it means when we have one-dimensional case, what is the differences between this one and a two-dimensional case. It means that you have the same cells on the other dimensions, or in this case, for example, the symmetry boundary condition here. What is the difference of that with this case, in this case, and a two-dimensional case? But what it describes here is indeed you have, imagine that you have vascularization or the consumption or the source of oxygen here with the initial concentration of C0, where X is 0, and then it starts to diffuse, and it can reach a point called here D, where you have no further concentration change in X, because in each point you have concentration changes, partial derivative to X, because it still diffuses, but at some point it ends. And this is indeed we can also call that the maximum diffusion depth. But in some cases, you can also assume that this is indeed a symmetry boundary condition because we have C0 at both sides. So make sure to understand symmetry boundary conditions, its difference with, for example, in this case, the maximum depth. Technically speaking, they don't have any difference, but you need to know how to apply them in the problems that you face. So we go on. In the for a steady state solution, we mean that it starts to diffuse, but it reaches a point that the diffusion ends, and you know that, okay, this is a profile of concentration that I will have forever. Just imagine like that. And then in this case, we know that there is no change of concentration over time. So we can say that we can easily ignore that term. And there is no temporal evolution term in the equation. Let's go on. And the question is, we want to obtain the maximum depth of oxygen penetration, as I told you. So how it starts, we have some coefficients. We have some derivative terms here, which is indeed in the second partial derivative, second derivative of concentration. So we want to get rid of that. How to do that? We have to do antiderivative operations, which is indeed integration. So here, it's also worth noting that I have simplified it, so I don't need to write all the things. So here, the rho is indeed the density of cells, and M is indeed the maximum consumption rate of oxygen. So we integrate the equation, integrate both sides, and this is indeed, according to calculus terms, it uses one order here, and here it's a simple equation, but we have one coefficient. One coefficient appears. How to obtain the value of this coefficient? That's simple. We can have a look at a problem and have appropriate boundary conditions. What boundary condition we can apply? We can go here. We know that when X equals D, the concentration of C, the concentration of oxygen doesn't change with X. So this term is 0 when X is D. So we can easily apply that and obtain and calculate the value of C1. We know that C1 is indeed this. So when we replace C1 with this value, we still see that we have some derivative terms. So we should continue the integration. We integrate this one, and then the derivative term will be eliminated. But we have a new C2 term here. I'm just going on relatively fast, but please ask question if there is something unclear, but also make sure to write it down yourself later on or with me at home and have appropriate practice to see how these things go on. This is relatively simple for people with background in engineering or science, mathematics, these kind of things, but maybe it'd be more difficult for others. But make sure, even you have a good background, make sure to write it down several times for different, not for one case, for different examples, and make sure that you know how to integrate various, at least the common forms of equations. So the next time, it's time for the next coefficient C2, again applying another boundary condition, which is very obvious here. We know that when C is C0, X is 0. So it can be simply applied like this. And then we know that C2 is indeed equal to C0, the initial concentration. So by knowing C1 and C2, we can go on and obtain the final equation. So we assemble everything together, and this is a final form of the equations, which can be also written as, for example, this. I have rewritten that to make it more simple to understand somehow. That indeed, you can imagine that C has a sort of parabolic profile here. That is indeed, it will be something like this. But then the question was how to find a maximum coefficient depth. We can say that, okay, in this equation, we can say when X equals D, we know that C is indeed in its maximum form. So I think when X equals D, C is indeed in its minimum, in minimum case, in this case, sorry. So let's do that. You can write this and also pay attention that this time D can be also denoted as D max, because we want to see the maximum diffusion depth. And so we know that C is 0 there because this is where it can reach. This is the maximum length that it can reach. So it is indeed 0 there, because if it was not 0, it could have gone a bit far. And by writing this, we have the maximum concentration depth as this. And this is the same value that you saw on the slides. So this is indeed how you can obtain this manually by writing that, step by step analytically. A similar problems, you should solve it as an exercise, but this is indeed even more interesting thing that related bone healing in large bone defects. In large bone defects, you may did the vascularization and supplies of oxygen is very crucial, but also the distance between the broken bone is also crucial to know. And you can see now that applying this kind of mathematical equations, this mathematical model can be a great tool to understand what happens there and what is the best situation to treat this. So what you need to do is derive an expression for penetration depth. We want to see how much oxygen is indeed required and what is the biggest length that this amount of oxygen can indeed be useful and be indeed crucial for the bone to grow. So another thing that you can consider in this exercise is as I told you, the symmetric boundary condition in the middle. Here, what kind of boundary condition you should apply in the gap, in the middle of the gap? Is it a symmetric boundary condition especially for large bone defects? You should consider segmental defects and defects and the way that you can apply boundary condition to that. So I said this is important. I have highlighted this here because when you face an exercise in the exam or in your career or in your future research whatsoever, what is really crucial is to find how you can describe the problem in mathematics. Here, in this case, in forms of reaction, advection, diffusion equation. The equation is always the same, more or less. But the thing is, what differs from one problem to the other one is indeed the boundary conditions. So make sure to understand different boundary conditions that you have seen in the slides, and also in this case, which is very similar to the cellular construct. And to solve that, you can use these relatively realistic numerical values for the diffusion rates, for the consumption of oxygen, for the cell densities. For C0, initial concentration of C, for example, in the bone or in the surrounding, this is very crucial, and you can see the different effects. So if you look at this mathematical simulation as a tool, this is indeed where it comes very handy, very useful for example, clinicians, for other people, for people in practical fields, that you can have a formulation like the expression that you derive here and then play with different conditions. For example, the minimum amount of oxygen that is indeed, it can be in the middle, and also the initial concentration of oxygen. So here you see that, for example, in this case, the boundary condition in the middle is not C equals 0, because you need a minimum amount of oxygen. And then you can see that according to, for example, the initial oxygen concentration here is of course, this is expressed in the terms of solubility. But then you can examine different conditions and see in which case the bone remodeling occur, because for bone remodeling, you need oxygen. But at the same time, also pay attention to this fact that oxygen, oxygen is not the only substance that the cells need. There are lots of other things like glucose, and it highly depends on the cells, on the type of cells. But in this case, we assume that it is only oxygen, so there are some simplification in the model. But this is indeed how a mathematical formulation works, how mathematical modeling works for a real application. So make sure to solve this on your own. And then if you had any problem, make sure to come back to me. Don't hesitate to come back to me by email. My email was in the first slide, and then we can discuss it. So what was indeed very important for the previous example that I showed you, and this one that I told you as an exercise, was indeed the solubility of oxygen. So in the exercise, oxygen was indeed expressed as a percentage. So you remember from the slides, make sure to just have a recap on oxygen solubility, that when you have the expressions on the diffusion reaction advection equation works based on concentration. But sometimes, especially in practice, in clinics, you have the expression for the oxygen or other components as solubility. as the tension or as a percentage, as you saw in the exercise. So make sure if you face that in the exam or face that in a problem that you want to solve in practice or in research, in whatsoever, make sure to have proper conversion. So I put it here to emphasize on the fact to pay attention to the units and also to the way that the quantities are expressed. So let's have another example. The other example could be the KU cylinder model of tissue oxygenation that you saw in a slide 22 of Hans slides, I mean. You saw that the general form, but what is indeed interesting here is that it is a bit different because it is indeed radial diffusion and in radial coordinates. So you should also be sure that you have good knowledge of different coordinates, and by knowledge I mean you know how to solve them, because practically technically speaking, this doesn't differ from like the diffusion in the Euclidean coordinates, in normal coordinate system. But in practice, this kind of stuff, as you will see, will become a bit more complex, a bit. So make sure to have one or two problems solved in this case to get yourself familiar with the concepts, with more complex forms of differential equations. More important, let's say, integrating them, as I will show you. So here, you have oxygenation. So the boundary conditions are so nice. Let's say it's obvious that here the oxygen is indeed, or for example, the amount of oxygen, the concentration of oxygen is 0. So when R is equals R0, C is 0 indeed. And when R is equals RC, the concentration is indeed CRC, let's say C of RC. So the amount of oxygen that the vessel, that is indeed the tube, in this case, the simplified model, this tube will provide for the tissue. So again, another simple but a very practical one when you can play with the parameters in the model. That's indeed where the benefits comes into play. So problem we want to solve is indeed this one, the diffusion rate we have, and as you can, and why it becomes a bit complex is because of this. For example, having the R, the independent here is indeed independent variable here. So when you integrate it, it becomes a bit different from the previous example that you saw. I will simplify the notations, make it a bit simpler to write down the equations. So the equation we want to solve is indeed this one. I also highly recommend you to simplify notation. So you don't need to, repeat all these things multiple times when you are writing it down on a paper or in the exam. So the procedure is exactly the same. We integrate the equation, integrating both sides to get rid of the derivative terms. Then we end up with a coefficient. So here we can apply easily one of the boundary conditions that we know here. We know that when R is equal to this R0, the diffusion, there is no diffusion. There is no change of, let's say, concentration. You see the beauty of applying boundary conditions. And this can differ from, example to example. Maybe you face another kind of, problem that, for example, they say that concentration is C0 here or C diff here, whatever. No difference for you. What you need to do is indeed applying this to the form of equations that you have after integration to obtain the coefficients here. So after having this, After seeing this, you can go back to the slide that I had for the steps you need to take to solve the problems and see what those steps mean. So let's go. Applying this is simple, and we can see that C1 is indeed in this form. We have still, if you replace this value here, we have still derivative terms here. So we need to go on and we integrate the term. I still have C1 here because C1 equation was a bit complex. I don't want to repeat it here, so I still write C1. The integration is here. We have the logarithm, ln logarithm in the scale of the natural exponent in the base of a natural exponent. So this is why I said that it will be a bit different. So after that, we go on and we apply the next boundary condition to get C2. So we know that when R is in its maximum, in this case RC, C is the amount of oxygen that you have there. And you apply it, and then you see that this will end up with this equation, and you can rewrite it to obtain C2. Okay, and then we can assemble everything together to get this equation. And this equation is exactly the same equation as you have seen in the slides of Hans, but you need to rewrite it a bit, and then you will have the same form. And then here you can have a wide variety of different output out of this, which you will find examples in the slides. I don't want to repeat it, but as I showed you here, the main benefit is exactly when you can play with the parameters to plot multiple combinations and see which combination is indeed the best to pick. Okay, so after having all these things, especially for the second example, you saw that it was a bit complex, even in this analytical form, to obtain the equations, to obtain the analytical solution of that. So you can use computers to let them solve the equations for you, even symbolically. So we want to talk a bit about how to use symbolic computing. If you're not familiar with that, it means that computers can do algebraic operations and manipulations for you. You may have not faced this concept yet, but I will show you. If you have faced, if you know what that is, then it's much better, because then you can immediately apply that to those equations. Then I can say that there are lots of options that you can use. MATLAB has not a very powerful, but a submodule for symbolic computing. Maple is the main one, is the most famous one that is really, is dedicated to symbolic computing. And Python is also a good choice because Python is becoming a dominant computing language. I will provide you with some materials here to get familiar yourself with Python, because I highly recommend you, as an engineering student, know Python. Python is becoming more and more popular if you want to go to industry. As an engineer, it becomes very useful. People now, this is, nowadays it's a must. Before that, it was a benefit for people, but now, when everyone knows that, it means that you should also know it, because you can take advantage of that in one variety of different things. Even if you're not dealing with computer simulations or mathematics, you can still use that for data processing, for data science, for automation, for optimization, lots of different things that you will face as an engineer. But in this case, because I don't want you to have, for example, complex things, command line things, programming things, I want to use Jupyter. Jupyter is an interactive environment for different programming languages that allows people to have an easier approach to programming. It's mainly intended to be used with Python, but it has also, extension for almost every programming language on the planet. I want to use that to make things simpler in this session. But I will provide you also with enough materials if you want to get to know, if you want to know Jupyter better, if you want to install it, go on and do that, especially if you are interested in these things, interested in computing, interested in solving equations with programming, or interested in programming in general. So as I said, learning Python is super easy. I have one document. I will provide you with the links here that will teach you Python in less than maybe half an hour, and you can easily go through that and learn all the essential things that you need to solve equations with Python, and also learn the essential topics of Python as well. So the material will be provided later. I have put the links in the slides, but in order to get started with that, there are two options that you can follow. You can install Jupyter, which consequently installs Python as well locally on your machine, on your laptop or PC. But yeah, this is a relatively advanced step. If you don't want to install it, or if you don't have, enough hard disk space, storage space, or you are not interested in having that installed because it's relatively an advanced step, you can go for the option 2. But for the people who are interested, I highly recommend installing Jupyter and give it a try, and try to go through that. You will learn a lot, and you will find lots of useful information and resources on the internet to take advantage of that, for a wide variety of different topics. Lots of educational materials and didactical materials are provided nowadays as Jupyter, in the Jupyter formats. Specifically, I can say Jupyter notebooks, because they call it Jupyter notebooks because they are indeed interactive, very interactive environments. The second option is running the examples on free online services. I will provide you with the links and the instructions. So if you don't want to install Jupyter locally, you can try this option, and then it will be much easier for you. You cannot save things. It's not very robust to do some real projects on these services, but to give it a shot, to just try it, this is the fastest way. So if you wanna, I will provide you with the information you need to run the examples locally, and also on those online services. So you need to go to this repository. If you know what GitHub is, that's very good. If you don't know, GitHub is indeed a service to host codes, to host resources, mostly related to open source projects. And this is indeed all the materials that I have provided for you are indeed all open source. So you can also take them and use them wherever you like. So you go to this repository. Let me also open that. Then the further step is you download the code. You see a code bottom there. I will show you, and then download the zip file. And then in a zip file, there is one installation guide. You can follow that, and then you can have Jupyter installed locally. And then you can watch the notebook 0 to 5. Let me show you what it means here. I hope you can see it. If you don't, please tell me. So this is in the bottom that you can, the button that you can download the zip, and by notebooks 0 to 5, I mean these notebooks. I will show you the content later. And then the next thing that you can use, the next option is running examples online. So you go to the same repository, and then you click on the launch binary badge below the title. And then you need to wait a bit. Oh, sorry. I didn't need to click on that. So you need to wait a bit until the server starts, and then you can run the notebooks interactively. So this is indeed what I want to show you now. So instead of having that locally, I can run it on this. So it takes a bit time to prepare the an installation of Jupyter. And then I can go on. If it takes too much, because yeah, it tries to install things. I can also go on with my local install. Let me run my local install, but at the same time, I will also check if that works. So this is indeed my local install, but I will show you that they are equivalent. So it takes a bit of time. Just copying things. But yeah, let me first show you the thing on my local install. So I go to folder of the repo. I have provided you with installation guide, how to navigate things. And this is indeed the main interface of Jupyter. When it starts here, which is still not started, you see the similar interface. So these are indeed my notebooks, Jupyter notebooks. And when I click them, you see that it starts like this. So this is indeed what I mean by having an interactive environment, interactive computing environment. So you see that I have codes, but at the same time, some description beside them, which allows you to run things interactively. Let me see if it is started. It hasn't started yet. It says that your session is taking longer than usual. I don't know. Maybe it's bad luck. But okay, I will go on with the local session and wait till the online one gets ready. So you see that here, I can run each cell individually. Like this is indeed a Python code that says, I will describe it later. That says, okay, from SymPy package, SymPy is indeed a symbolic computing package Python. Import this function and it initializes a session. So I run it, I click on this run button here, and when a number appears here, it means that it's being run. So then you can see that I have said that let's have an integral. So I run this one as well. So now I have f and a, and a is indeed the integral of f. So I displayed it here. It shows me that this is indeed this equation, and it solves that for me. This is how symbolic computing works. You can see that I can have the integration of this equation symbolically, and also its derivative differentiation as well. So this is indeed the differentiation, and this is the integration. And you can see that I can employ this technique to, more or less solve the equations that I showed you for mass transport in a cellular construct, and also for the Krog cylinder. When I say that it is interactive, it means that, for example, imagine that I want to change it to 2. This is in the check installation. You should go through this to make sure that your installation is okay. Then I have to run this one and then run this one again. And you see that this time the equation, the exponent is different. And also this one. So this is indeed how Jupyter works. You have an environment that you can have the descriptions and the codes together, and you can run the codes interactively directly there without being worried about installation of Python or installing dependencies, this kind of stuff. It takes care of that. Let me have a look if my online, oh, finally it's ready. So you can see that in the online version, I have exactly the same thing, the same interface. So this is indeed the online version. I can click on each notebook and they open here. So I can here say cell run all, and you see that it works on the online version. So that's exactly the same with some limitation, of course, but it's exactly the same as my local install. So you can go through this or simply use the local version. So I will go on with my local version again, but yeah, you can use the online one. So I don't want to say that. So these are the content. The first two are indeed Introduction to Python Programming and Introduction to SymPy. I have provided links to the main course, to the main repository that I have taken these two from, because there were lots of others, different aspects of Python programming, different packages, very useful packages for scientific computing, for computing and engineering, for symbolic computing, for numerical computing, for plotting, for lots of stuff. But I have taken just SymPy because this is indeed what we want. If you are interested in more aspects, you can go on and take them. And now you also see what I said, that this is indeed, Jupyter is very useful to learn things because you find useful information on the internet. People have already shared them. And it's different from, traditional books where you read things and they have codes there and you need to, type the code somewhere else. Sometimes they provide the codes, they provide the techniques, but you need to install things and go and run them yourself on command line or in another program. But here you have everything together. So you have the descriptions and you have the codes, as I showed you, to run them yourself, to run them. But anyway, this is the introduction to Python programming. I don't want to go through this, to all the aspects. I want to just show you how different section it has and maybe just highlighting the most important ones. So in Python, we have modules. It says most of the functionality of Python is provided by modules, and SymPy was indeed one of them that we want to use for symbolic computing, but there are lots of others. This is in the beauty of Python, that for, for most of the aspects of computing, automation, engineering, you can find relevant packages, and someone has developed something and put it on the internet, so you can take advantage of that. So here it says that, for example, from the math package, or you can use it as import, or from, with the syntax from math, import everything and the cosine function of 2pi, and then it says that it is 1. So this is the way that you can load packages. This is not, you can go through this yourself. But for the variables assignment is very similar to MATLAB. You don't need to define the type of the variable, so that they are automatically assigned. And in computer science, this is called dynamically typed language, which means that the language will automatically detect the types of the variables. But you can ask for the types, and it says that, for example, x is indeed a floating point, and x here is an integer. There are fundamental types here, but as I told you, they are automatically assigned. So you have Booleans, you have complex, you have strings, you have integers, lots of stuff. Let's go on for the typecasting. You can cast between typecasting, means that you can convert one variable to the other one. This is not something that we want in this course. I told you, you can go through this yourself and enjoy that. But I want to just emphasize the things that we need here in this section. So these are the operators. You see that they are very similar to MATLAB. If you know MATLAB, you find this very similar to that, and you feel that you are in something that you know already when you work with Python and Jupyter. So these are the comparison operators. We have strings in MATLAB, in Python, and here it says that it's very similar to the way the MATLAB handles them. But the only difference is very similar to other more professional programming languages. The indexing starts from 0. This is for a string comparison. In Python, we have lists, very useful feature. I think we have that in the example for symbolic computing. But lists, you can see a lot of lists, and this is one of the great tools for automation. You see in lots of codes, Python codes, that they take advantage of lists. It's one of the most important data structures. And then modifying, adding stuff to the lists, they are pretty simple. You know, if you go through this, you find it that, as I told you, as I claimed, Python is very easy to use, very easy. It surprises you that how easy it is. For the tuples, this is a bit advanced, but here dictionaries is something that you will see in the symbolic computing. It's a data structure that I think MATLAB also has. I don't know the name in MATLAB, maybe cells, maybe, I don't know, or structures, maybe in MATLAB. But here they are called dictionaries. It means that this is a list, but each list has a key and a value, key value, and then you see that you can easily call that with this notation. So with list, with arrays, you have index. The index is number. You say that the second, for example, second member of the array, I want that. But here you say that the member of proms here with the key of the prom is 1, and it tells you that, and then you can change it. This is pretty handy in symbolic computing as well. And then it goes to control flow, how to control the flow with loops and with conditional statements like if, else, pretty simple. What is really important in MATLAB, in Python, that is a bit challenging for the people who just start to use that, is following the rules of indentation. It means that, for example, in this case, it works, but if I say that, for example, you see that I run it and it runs, but if I remove this indentation, then it gives me an error. That it says that expected an indent and block here, because below if it's very similar to the codes in C and C++, then you need these curly brackets. But here, instead of those things, you need to have an indentation, or even having multiple indentations, as you see here. This is something you need to follow. You will find it very easy. And when you start to use that, you see that it's much easier than any other programming language. But yeah, it takes some time for people to, you know, be more convenient with that. So also loops. Loops are very similar to MATLAB in comparison to other programming languages. So, you know, for example, here you say that for x in range 4, it will be something like this. And for x in 1, 2, 3, it's like this. So the range can be also different. And you can also iterate through lists here. And also dictionaries. So these are the things that I wanted to show you. You can go on with this tutorial yourself. If you're interested, I recommended you to do that, but it's indeed your choice. I just described the things that are essential for us for symbolic computing, but there are also other essential things. And for SymPy, I showed you some parts of the codes of SymPy, but how to do symbolic algebra in Python. So from SymPy, I import everything, and then we init the session or init printing in order to have LaTeX-like stuff here. You can see that here, the variable, we define them with symbol. So x is a symbolic variable. So when I say pi plus x squared, it becomes something like this. And you can define multiple symbols. And sometimes you can say that it is a real number or it is positive. This is something that we will use to apply boundary conditions. And then you can have complex numbers, rational numbers, and sometimes you need numerical evaluation of things. Like, for example, you can say pi, evaluate pi because pi is something symbolic with 15 numbers. And you say that y is, for example, is x plus pi squared, and you want to evaluate y with 5. But if you want to substitute, you want to know the value of phi. If x is, for example, 1.5, you should use this sub function, which we'll use a lot in our symbolic computing things. Then you can have, for example, replacement of x with this value. And here is the way that you can plot things. And then this is indeed the most interesting part, how you can expand. For example, you say that this is indeed my equation, this is my expression, and then you call it with expand, call the expand function, and it tells you that how it looks like after it is expanded. And it can even be used with trigonometric functions like sine of a plus b, and when you expand it, you know this is the famous sine rules. And similarly, but in the inverse order, you can have the factorization, which is indeed the inverse operation to going from the expanded form to the cosine form. And you have simplify, and you know, for example, everyone knows, people with a background in mathematics and engineering know that cosine and sine is indeed one on tangent or cotangent. So this is indeed what a simplify does. And then also you can, you know, for fractions, you can have a part and together. But this is what we want, calculus. What I suggest is you go through this, but run the commands yourself. So here I have already run all of them. So you have the output here, but make sure to run them. And also at some points, change these things as I show you. Change these values yourself and then click around bottom to see what happens. For differentiation, it is diff, and for integration, it is indeed integrate, as I showed you in the first example. So this is very important for us to define our differential equations. And then for the integration, we want the integration to go from the conservative form of equations or mass transport things to its plane mode, to the form that has the coefficients. And then you have sum and products. We don't need that in these things. I put them here for you to know. And then limits and series. And then what is also important for us, and here is matrices. We don't need that. Here, solving equations. So we want to solve equations later on because we want to solve the differential equation and then solve some algebraic equations to obtain the integration coefficients. So we will use solve. You can see here x squared minus 1. It says that solve this for x. And it means that x can be minus 1 and 1. And it can also solve more complex equations, including also imaginary forms. So this was indeed, these were introductory things. I didn't spend lots of time on that because I want to go here for the mass transfer in cellular construct. This is the example that I showed you. I elaborated a solution. So we want to solve this, and as you can see, you can also write equations easily here in Jupyter. So this is what I've done for you to make it simpler to follow the solution here. But then you saw this in the slides. I showed you integrate. We integrated, and then we apply the first boundary condition to obtain C1, and then we apply we continue the integration. We apply the second boundary condition. We assemble everything together. And then if we want to know, for example, the maximum depth of diffusion, we can get it simply. But let's see how we can solve it with SymPy. I haven't put a description here because this is relatively self-descriptory, but the description is exactly the same as this analytical solution. So I import SymPy, and then I define this x, d, v, and rho with symbols. And then I define a function c, and the ODE, which is indeed this one, or this one, is defined here. You can compare the code with the analytical solution to see that how this implementation works in SymPy. And you can see that this is, for example, simple. We can say that d multiplied by c of x, but its second derivative, differentiation to x, but in the second order, minus v multiplied by rho. So it shows me the equation like this, but then I call the function dsolve, differential equation solution. And it solves the differential equation for me. You can see that it gives me the form that I got with 2 levels of integration directly. That's why I told you that you can solve more complex problems with this, problems that you cannot solve analytically, or the analytical form becomes very complex. So after that, I need to apply my boundary conditions to obtain the C1 and C2, and this is what this piece of code does. So I define the C0 and D, and you see that these are in the dictionaries. That's why I told you that for the dictionary, this is a dictionary indeed. In the Python data structures that I told you, that you say C1 is indeed C0, and when the derivative of C at the point D is 0. This is our second boundary condition. You know, the derivative of C where x is D is 0. And this is how we can define it in Python and in SymPy. And then I apply them with the subs, I told you, with subs on the equations. And then we have these 2 equations, which are very similar to the equations that we solved to obtain the C1 and C2. And then we call this solve function with the parameters on the equation, and it gives us the value that we got analytically. Isn't it beautiful? This is indeed very nice, I think. And then by replacing those parameters in the main equation, this is the form of the equation. And how to get the maximum concentration diffusion depth? It's very easy. We can say that we want to see where 6 is 0, and then solve. It gives us this equation, and then we call solve again, and it tells us that this is indeed the diffusion, the maximum diffusion depth. And the equation is indeed exactly as this one. So this is how you can use SymPy to solve equations. And make sure to check first, write down the analytical form yourself, and then check this Python implementation with what you have written on the paper to see how it works. And then you can learn this. It's easy to learn. And I have implemented also the Croc cylinder example. So here is the analytical form. You can see that we derive a relatively more complex equation here. But then we can simply solve it with SymPy in an exactly same way as we did for the cellular construct. So we define things, and then we defined our differential equation here. So this is our differential equation. You know, the format is a bit different, but we don't care. So we call dsolve, differential equation solve. This is the form, and log here is I've said here that is indeed an ln function in mathematics. And then we apply the boundary conditions with dictionaries, and this is indeed the equation that we need to solve to get them. And there are C2 both sides, and we don't care because SymPy will take care of that. And we solve them, and these are indeed the value of C1 and C2 that we had in these slides and also here. And when we assemble everything together, it tells us that this is indeed the value of CR, which is the same as what we derived and what you saw in the Hans slides. So this was indeed how Jupyter can help us to visualize things, to get started faster, much faster with Python, and how SymPy will help us to perform symbolic computing in Python to solve differential equation problems, diffusion problems. But then, as the last topic to cover, what if the problems get more complex, like transient problems? How we can solve them? We care about this. This is very important because in real application models that you can see in tissue engineering, in wide variety of different engineering fields, mechanical engineering, civil engineering, material science, natural sciences, lots of stuff, lots of fields. The real models usually contain complex terms, and they are not steady state, they are transient. And they cannot be solved analytically. Why? Just have a look at this equation. For a two-dimensional case of a diffusion problem, just imagine that you want to solve this analytically. How you want to integrate both of these together? Just try that yourself, and you will see that it becomes very difficult. And just imagine that you have more terms here that then you have reaction terms, or even more difficult, the advection term. Then you cannot solve it analytically or with SymPy or with these tools. There are a limited, set of solutions to very simple equations. I mean, diffusion equations, but they are not really practical. You cannot solve them and get the, values over time, because here you want a value over time. What it means by over time, you saw lots of simulations in the beginning of this presentation, and they were all very like something like this, that you see that it diffuses, how it sees in the diffusing in the space over time. Temporal diffusion. We had the temporal evolution, remember, from the equation, and this is this term that we have here. So how these kind of simulations, how these animations are produced, this is where numerical computing comes into play. You have seen this type of mesh and this type of figures a lot in engineering, in computational engineering, when people use computers to solve equations. And this is indeed, the relevance of that. This is what it represents. So it means that we want to solve the equation numerically on a mesh. I will describe what I mean by numerically. But as I told you, this has a wide variety of different applications in a broad range of engineering fields. Let me give you some examples in tissue engineering. For example, you can use this kind of models. You can use this kind of numerical simulations in tissue remodeling, or oxygenation for the cases that we solve analytically. But imagine that you have more terms, like you have the time-dependent terms, temporal evolution term, and you want to see what happens over time. You don't want to assume that it reaches a steady state situation. You don't want to assume that. You want to see what happens over time. And for example, for scaffold degradation, that is indeed related to my PhD work, the figure that you see at the bottom here. So we have, for example, the tissue engineering scaffold, but over time you want it to disappear and be replaced by tissue. So for this one, we have a relatively complex equation that we cannot solve analytically. And then cell proliferation and tissue growth, which is in the example above this. This one, you have scaffold, this grain, this dark region, and then cells on top of them that are indeed seated start to proliferate. A great example in tissue engineering, but it comes with complex equations that they are indeed in a format of reaction, advection, diffusion form. equation, sorry, but how to solve them to get these things. And another example can be cell viability, which is indeed the example that I want to show you, that I want to present to you here, and lots of others. So cell viability for pancreatic islets. So I have a reference for this in the end, so you can, if you are interested in that, you can go and read more about this. But this is one of the ways to treat type 1 of diabetes, and diabetes, the most severe form of that. So when you have some cancer, some misfunctioning of pancreatic cells in pancreas, you prepare some islets in some specific devices, and then you transplant them into the patient. But these devices, I don't want to go to the details of the clinical relevance of this, but then the problem is, will the implanted islet survive or not? But it's really crucial for cells. Islets here means a group of cells, and a colony of cells, lots of cells into one. They just gather together. They just put together, and then they form something they call islets. And I want to see if they survive. So they put them inside some wells, some holes, you see here, and they provide oxygen through their boundary. As you know, simulated environment for the islets, for culturing them, to prepare them to grow and be ready to be transplanted to the patient. So this is what happens in the clinics. But then using numerical computing, or let's say mathematical modeling, we want to see if the islets survive and what is the perfect condition, because from the economic perspective and also from practical perspective as well, they want to put more islets into wells to have more cells in a small surface, in a small amount of space, let's say. But then the question is, will they survive? Is the provided oxygen enough for them or not? And then this is when we can model this with mathematics and play with the parameters, play with different conditions. The mathematical model of this clinical model consists of a reaction, diffusion, advection equation, but it is in nonlinear form because of these reaction terms, which makes it a bit more complex. So here is indeed a reaction term. This is diffusion, temporal evolution, advection. Reaction term is very similar to Michael-Menton form of reaction terms that you saw in the slides in the main course, which correlates lots of things: the concentration of glucose, the concentration of oxygen. It has one termination term here, which says that make this 1 0 when the concentration drops below a critical concentration. And then we define a critical concentration and we want to see if the cells, the rate of consumption of oxygen and the diffusion of oxygen will lead to a situation where it drops below a certain threshold. So this is indeed the goal of having this mathematical equation. But apparently we cannot solve it analytically. That's very difficult. So we solve that using numerical computing. So in this case, you see that we have one islet and then two islets with different sizes. And this is indeed where on the right, on the left, it reaches a steady state after some time. And you see that, okay, this is indeed how the provided oxygen. Here you see that it creates a profile of concentration. You have enough oxygen here on red, and then very low oxygen concentration here in the center of those islets. And then we want to see what happens if you put two islets together. What is the profile of oxygen consumption here? So yeah, this is how we can what we can really get from this kind of simulations. But then let me go. Yeah. Okay, sorry. So then, beside this nice graphical representation, what is the real benefit is we can have, for example, a plot over line here, a plot over line of change of oxygen concentration, and this will be something like this. And then we want to see if the oxygen concentration here is indeed solubility drops below a certain threshold, which is in this case hypoxia, and the cells cannot survive. The cells cannot survive; they die. And by having these curves, we can have, we can have the most optimal situation, most optimal setup and configuration to putting islets together. And it means that we can test a wide variety of different conditions, changing the size and distance of islets in multiple simulations. And that's very easy after you implement the model and you solve the model either by an analytical form, by an analytical solution that is apparently impossible in this case, as you saw, or the numerical implementation. But then the question is how it works. I mean, the numerical approximation. You saw also a couple of slides in your presentation in the main slides of the course for computational fluid dynamics, and this is very similar to that. So the core idea, for example, to solve this diffusion equation, the core idea is to approximate. This is indeed very important. Approximate the derivation terms on a discrete space and time. Discrete space means the mesh. The mesh things, the grid that I showed you also in the slides, and you have seen them a lot in lots of presentation. And it might be also your master project, your master thesis project. So you know what a discrete space is. But approximation means that we should pay attention to the fact that all the solutions that we obtain here are indeed approximations in comparison to analytical formats, analytical solution, that this is the exact solution according to mathematical model. Here, the model is approximated. What it means, pay attention to this. Imagine that if we have a function of x, which is in this blue curve, and we want to obtain the slope of this function at x, xj. Just assume that this is xj, a point, arbitrary point here. What we are interested in is slope, because you know that the slope means it's derivation, differentiation. So, for example, imagine that we have the derivation regarding time with respect to time, or derivation respecting differentiation respecting to x, even with the second order, third order, or the first order. So the slope is this black line. This is the true slope, the exact slope. But then you see that if you go a bit further forward and a bit backward and evaluate a function there and connect them, the slope of this red line is an approximation to that black line, isn't it? So we can say that in order to evaluate the differentiation, the value of differentiation of f of x at xj, we can go a bit forward and a bit backward and evaluate this slope. And this is why we say that this is indeed an approximation. It becomes it becomes more accurate. You can increase the accuracy by bringing these nodes closer to this. And this is why when your simulations, when you perform numerical simulation, they say you can increase the accuracy by increasing the mesh, the number of elements, the number of the mesh nodes, or decreasing the mesh size. This is indeed irrelevant. So in computational works, you usually see these concepts. So let's see how it looks like when we apply that. In 2D, it becomes something like this. So just imagine that, for example, for the diffusion examples that I showed you, or for cell viability, it was in 2D space. In 3D, it becomes 3D with the z-axis added. But in 2D, you can have a beat forward, a beat backward, a beat upward, and a beat downward. So by having the value of u at different nodes, doesn't it remind you of mesh, of computational mesh that I showed you, that you see in lots of computational studies in science and engineering? This is indeed the concept. And then you can easily say that, okay, we can approximate these terms here. This is indeed very simple. This notation on the top is indeed for time. So for time, just imagine that you have a similar thing. This time is a bit fictional. So for time, you have the same concept with the previous time step and the next time step. And this is a bit different from the slope of this because this is a second derivative. For second derivative, you need to repeat this 2 times, twice. So by reordering this, you can see that we can have the value of u at each point. So we repeat this equation for each point and for each time. So we need 2 iterations, and then we can have the value of this approximated. That's pretty simple, especially from the implementation perspective. So a simple implementation, as I told you, it can be implemented in Python very easily. So here is one example. It is related to temperature, but it doesn't have any difference. It's diffusion of temperature. You can look at that as a diffusion of concentration of a species or ions or whatsoever in mass transfer. Or in the cellular constructs, they're very similar. So here I have this implementation in the Jupyter format also. You can check it out, but it shows you how, for example, in the initial condition, and then it goes here. And then over time, we can have a solution. And you can see that the diffusion is in both directions, outward and inward, because it also starts to outward, it starts to grow, and downward, it starts to be, somehow used, let's say. It releases that. We have concentration of mass, or conservation of mass and conservation of heat. It means that the amount of heat is always the same if it is not generated or it is not consumed, or same for mass. So when it goes out, it should be consumed inside. And that's why you have yellow here. So I've said here, check out the full implementation in the Jupyter, because this is the 5th notebook is related to this one. I show you that. So the same formulation, more description. For making simulation stable, the technical term is convergence, but you don't need to care about that. You need a special consideration for the amount of time step that you choose here, because then everything is approximation. In the slides, you saw delta x and delta y, but delta t means how you want to go to the next time step. What is the distance in time between each time step, between each time point? So you see here that you can easily implement this equation in Python using 2 indeed nested loops. For I and j in nx and ny range, you can calculate that, and that's very simple. So you can easily simulate even complex equations like this using numerical computing. So here is the full implementation. Of course, this is more efficient implementation. They have used some MATLAB log notation for indexing to make the computation faster. And then it starts to plot the results. So if you follow the first 2 introductory notebooks, you can easily have you can easily understand this implementation. And when I run it, it produces this this output that was indeed the same as this light. So that was indeed all the content that I wanted to present. I hope you enjoyed that. If you get interested, make sure to go through the materials that I have provided and try to learn it. You can always reach me. You can always reach out by sending an email to me. I told you can find my email in the first slide, but also feel free to ask any question right now or send me an email afterward.